right, so get this. You challenged me with Stephen Hawking's A Brief History of Time for this deep dive.
Oh, wow.
Talk about a book that's captured imaginations of, well, pretty much everyone, and it's even outsold Madonna,
I did hear about that.
which Hawking himself found pretty hilarious. But you know what's even more fascinating? The way he explains the universe, time, black holes concepts that could make your head spin, but he makes them, dare I say, fun.
Hawking did have a knack for making complex physics surprisingly approachable.
It's true, he kicks things off with this story about a scientist explaining how the Earth orbits the sun and the sun orbits the galaxy, and a little old lady in the audience pipes up and says, "Nope, the world's a flat plate on a giant tortoise."
Ah, yes, the classic turtles all the way down idea. It's a funny way to highlight how our understanding of the universe has shifted over time.
Yeah, it makes you wonder, what will people be chuckling about 100 years from now when they look back at our ideas about the universe? But before we get too ahead of ourselves, let's rewind a bit. For centuries, people believed in Ptolemy's Earth-centric model, the one with Earth at the center of everything. But even Ptolemy knew there were problems with this model. He realized it predicted the moon should sometimes appear twice as large as at other times, which obviously isn't the case.
Even the greatest minds can sometimes cling to flawed ideas, especially when they fit the prevailing worldview.
Right.
But then comes Copernicus, proposing a radical new idea, a sun-centric model with the sun at the center. And get this, he initially circulated it anonymously. Can you imagine being that afraid of challenging the status quo?
Talk about a scientific mic drop, but it took more than just a revolutionary idea to convince people. It took evidence. Enter Galileo, who used the newly invented telescope to observe Jupiter's moons orbiting Jupiter. That was a pretty big deal, right? Because it showed that not everything revolved around the Earth after all.
It was a pivotal moment in our understanding of the cosmos. And then Kepler refined Copernicus's model further, suggesting that planets move in elliptical orbits rather than perfect circles. Suddenly, the predictions started matching the observations with remarkable accuracy.
So step by step, our picture of the universe began to change. We moved from a stationary Earth at the center of everything to a dynamic solar system with planets orbiting the sun, but then Einstein steps onto the scene and things get even more interesting.
Einstein's theories of relativity completely revolutionized our understanding of space and time. He showed that these concepts weren't absolute, as we'd always assumed, but relative.
Okay, I've heard about relativity, but I'll admit it's always felt a bit intimidating, like time being relative. What does that even mean? Does that mean time travel is possible?
It's definitely a mind-bending concept. Think of it like this. Imagine you're watching a ping pong ball bouncing on a moving train to you on the train. The ball just goes up and down, but to someone standing on the platform, the ball also has a horizontal motion as it moves along with the train. Both perspectives are valid, even though they describe different motions.
So it's about perspective, like how we perceive motion depends on where we are and how we're moving relative to the object.
Exactly. And this idea of relative motion extends to the speed of light. A key insight from Einstein's theory of special relativity is that the speed of light is constant for all observers, regardless of their own motion. This seemingly simple idea leads to some incredible consequences, including the notion that time itself isn't absolute.
Wait, hold up. Time is an absolute. You're saying it can actually be affected?
That's right. One of the most important experiments that paved the way for special relativity was the Michelson-Morley experiment. They were trying to detect something called ether that was thought to be the medium through which light traveled. The idea was that the Earth's movement through this ether would cause variations in the speed of light. But to their surprise, they couldn't detect any difference.
So no ether, does that mean light just travels through nothing? And how does this tie into time not being absolute?
Essentially, yes, light doesn't need a medium to travel, and the fact that the speed of light is constant for everyone no matter how they're moving means that time itself must be flexible. It can be affected by things like gravity and motion. It's a mind-blowing concept that's been experimentally verified.
Okay, I'm trying to wrap my head around this, but if time isn't this universal constant ticking away at the same rate for everyone,
Right.
what happens to our perception of past, present, and future? Does it all just become a jumbled mess?
It doesn't quite get that chaotic. Think of the twins paradox. Imagine one twin stays on Earth while the other travels at high speed in a spaceship. When they reunite, the traveling twin will actually be younger than the Earthbound one because time passes slower for objects moving at higher speeds relative to a stationary observer.
Okay, now my brain is officially starting to melt. So you're telling me that time travel, at least in a theoretical sense, is possible because time isn't this rigid, unchanging thing we perceive it to be.
It's certainly a fascinating implication of special relativity. While achieving those kinds of speeds for a human being is still firmly in the realm of science fiction. The very idea that time can be warped is mind-boggling, isn't it?
It definitely challenges everything I thought I knew about how the universe works. So if space and time aren't these separate absolute things, how should we think about them?
Hawking suggests a shift in our thinking. Instead of separate space and time, we need to embrace the concept of space-time, a unified four-dimensional fabric. It's like this. We can describe a point in space with three coordinates: length, width, and height. To describe an event in space-time, you need to add a fourth coordinate: time.
Okay, a four-dimensional world. I'm trying to visualize that, but it's definitely a stretch. Are there any ways to make this concept a bit more tangible?
Hawking uses the idea of light cones to help visualize how events in space-time relate to each other. Picture dropping a pebble into a pond, ripples spread out from where it hit in a circular pattern that expands outward. Right now, imagine that ripple pattern expanding in 3 dimensions, forming a cone shape. That cone represents the path of light emanating from an event in spacetime.
So the ripples are like light spreading out from that point in space-time. I can kind of see that. But how does this help us understand things like the past and the future?
The light cone defines the future past, and elsewhere, relative to a specific event, anything inside the cone's expanding future section represents events that could potentially be influenced by the original event. Events within the cone's past are those that could have influenced the event. But anything outside of these cones lies in the elsewhere, a region that can neither influence nor be influenced by the event because information can't travel faster than light.
So if something happens outside of my light cone, it's essentially in a separate reality, at least as far as I'm concerned. It's a strange way to think about things, but it makes a kind of sense. But, we've been focusing on special relativity, which deals with constant speeds. What happens when we throw gravity into the mix? That's where general relativity comes in, right?
That's right. General relativity goes a step further by explaining how gravity affects this space-time fabric we've been discussing, and it leads to even more mind-bending implications.
Okay, I'm ready for the next layer of mind-blowing. Hit me with it. How does gravity warp this space-time fabric?
Think of it this way. Imagine a bowling ball on a trampoline. It creates a dip, right? Objects don't move in straight lines because of some mysterious force pulling them toward the bowling ball, but rather because they follow the curvature of the trampoline created by the bowling ball's presence.
So you're saying gravity is like a cosmic bowling ball warping the space-time trampoline.
It's an analogy, but it gets the point across. In general relativity, gravity isn't a force acting through spacetime, but a consequence of mass and energy, warping the fabric of spacetime itself. Objects then follow the curvature of this warped spacetime, moving along paths called geodesics, which are essentially the straightest possible paths in this curved spacetime.
So gravity isn't just a force, but a fundamental property of the structure of the universe itself. It's pretty profound when you think about it. But does this actually have any observable effects? I mean, can we see space-time being warped by gravity?
Absolutely. One of the most famous examples is the bending of starlight around the sun during a solar eclipse. Einstein predicted this effect, and it was later confirmed by a British expedition in 1919. Although their measurements weren't as accurate as they thought, subsequent observations have definitively shown that starlight does indeed bend as it passes by massive objects, providing further support for general relativity.
So we have this incredibly complex interplay between gravity and space-time, but we're still just scratching the surface of the universe's mysteries, aren't we?
We've come a long way, but there's so much more to explore, and to delve deeper, we need to consider another fundamental theory that governs the universe: quantum mechanics, the science of the very small.
Okay, bring on the quantum weirdness. I'm ready to dive into that after a
Oh,
quick break to process all these incredible insights about space-time and gravity. Be back soon.
sounds good.
All right, I've caught my breath after that mind-bending dive into space-time and gravity, but now I'm curious, how do we even know that the universe is expanding in the first place?
That's a great question. It all comes down to something called redshift. You know how the pitch of a siren changes as an ambulance approaches and then passes you? It sounds higher pitched as it comes towards you, and then lower pitched as it moves away.
Yeah, like a wee sound. I've always wondered why that happens.
It's called the Doppler effect, and it happens with light waves too. When a light source is moving away from us, the wavelengths of light get stretched out, shifting towards the red end of the spectrum. That's redshift. And when astronomers observe the light from distant galaxies, they notice that it was consistently redshifted.
So it's like the galaxies are all playing a giant game of cosmic dodgeball, flying away from each other, and the farther away they are, the faster they seem to be moving.
That's a great way to put it. This redshift observation is one of the key pieces of evidence supporting the idea of an expanding universe. And it ties into the work of Alexander Friedman, a physicist who used Einstein's theory of general relativity to develop models of the universe.
Mhm.
He proposed three main types of models, each with a different fate for the universe. One where it expands and then recollapses, one where it keeps expanding forever, and one where it's perfectly balanced between those two outcomes.
So which one is our universe? Are we on a cosmic roller coaster ride that eventually ends back where it started, or are we on a one-way trip to infinity?
Current observations suggest that our universe is destined to expand forever, though it's still an area of active research. But what's even more fascinating is that all three of Friedman's models point back to a time when the universe was incredibly dense and hot, crammed into an infinitesimally small point.
Ah, the Big Bang.
Yeah.
So Friedman's models helped lay the groundwork for this idea that the universe started from this incredibly extreme state and has been expanding and cooling ever since.
It's exactly. The Big Bang Theory explains not only the expansion of the universe, but also the abundance of light elements like hydrogen and helium that we observe today. These elements were forged in the intense heat and pressure of the early universe, just moments after the Big Bang. It's a remarkable testament to how much we can learn about the universe's history by studying the composition of the matter around us.
It's mind-blowing to think that the very elements that make up our bodies were created in these cosmic furnaces billions of years ago. But let's back up a bit. If the universe started as this incredibly hot, dense point, what happened next? How did we get from this cosmic soup to stars, galaxies, and eventually planets and life?
It's a complex process, but here's a simplified version. As the universe expanded, it cooled down. Imagine a pot of boiling water cooling as you pour it into a larger container. That's kind of what happened with the universe about 1 second after the Big Bang. The temperature was still incredibly high, about 10 billion degrees hot enough to power countless H-bomb explosions at this stage. The universe was mostly a swirling mix of photons, electrons, neutrinos, and their antiparticles, along with some protons and neutrons.
So all the building blocks of matter just buzzing around in this incredibly energetic cosmic soup.
Precisely.
Yeah.
And as things cooled further, these particles started interacting and changing, for example, electrons and their antiparticles. Positrons began annihilating each other, producing more photons. Meanwhile, neutrinos, which are very weakly interacting particles, mostly just kept zipping through the cosmos.
So it's like a cosmic dance with different particles coming together, colliding and transforming.
A very energetic dance. Around 100 seconds after the Big Bang, protons and neutrons started combining to form deuterium and then helium, along with tiny amounts of lithium and beryllium.
So most of the helium in the universe was created in those first few minutes after the Big Bang.
That's right. It's one of the strongest pieces of evidence supporting the Big Bang Theory. And what's even more remarkable is that the proportions of these elements predicted by the Big Bang model match the proportions we actually observe in the universe with incredible accuracy. It's a powerful confirmation that we're on the right track in understanding the universe's origins.
It's amazing how much information we can glean about those early moments of the universe by studying its composition. But how did we go from this swirling soup of particles to the structured universe we see today with galaxies, stars, and planets?
Well, even in this incredibly uniform early universe, there were tiny, tiny variations in density. These fluctuations, some of which we can still observe in the cosmic microwave background, radiation acted as seeds for the large-scale structures we see today. As the universe expanded and cooled, gravity would have caused denser regions to pull in more matter, eventually leading to the formation of stars and galaxies.
It's incredible to think that these tiny imperfections in the early universe were essential for the formation of everything we see around us. It's like a cosmic domino effect, with those tiny initial variations setting off a chain of events that led to the complex and beautiful universe we know today.
It truly is a testament to the interconnectedness of everything in the universe.
Hmm.
And as stars formed, they acted as cosmic factories, fusing lighter elements in their cores to produce heavier elements like carbon, oxygen, and even iron. These heavier elements were then scattered throughout the universe when massive stars exploded as supernovae, enriching the cosmos with the ingredients necessary for the formation of planets and eventually life.
So we owe our very existence to these incredible processes that happened billions of years ago, from the Big Bang to the formation of stars and the creation of heavier elements. It's a humbling and awe-inspiring thought, but I'm realizing that we've been talking about the universe on a grand scale. The Big Bang, the expansion of the universe, the formation of galaxies. What about the world of the very small? Does quantum mechanics play a role in all of this?
Absolutely. In fact, to fully understand the very early universe, the extreme conditions near black holes, and the ultimate quest for a unified theory of physics, We need to bring both general relativity and quantum mechanics into the picture, and that's where things get even more fascinating and mind-bending.
Okay, I'm ready to venture into the quantum realm. What strange and counterintuitive ideas await us there?
Prepare to be amazed. Quantum mechanics is a world where particles can be in multiple places at once, where uncertainty is fundamental, and where the very act of observing something can change its reality.
Sounds like we're about to enter a whole new dimension of weirdness. Let's dive in.
Yeah.
Okay, I'm ready to enter this quantum realm you've been teasing, but I have to admit, quantum mechanics always makes me feel a little like Alice tumbling down the rabbit hole.
It's definitely a world that challenges our everyday intuition, but it's also incredibly beautiful and elegant in its own way. Quantum mechanics governs the behavior of matter and energy at the atomic and subatomic levels, and it's full of mind-bending concepts that defy our classical understanding of the universe.
So, where do we even begin? What are some of the key principles of quantum mechanics that we need to grasp to understand its impact on the universe?
One of the foundational principles is Planck's quantum hypothesis, which revolutionized physics in the early 20th century. It states that energy isn't exchanged continuously, but rather in discrete packets called quanta. It's like saying you can't dim a light switch gradually. It's either on or off quanta or nothing.
So, energy comes in these tiny, indivisible bundles. That's so counterintuitive in the everyday world. We're used to things changing smoothly and continuously.
It is strange, but numerous experiments have confirmed the quantized nature of energy, and this idea has profound implications. For example, it helps explain how atoms can be stable in classical physics. Electrons orbiting an atom should continuously lose energy and spiral into the nucleus, causing the atom to collapse. But thanks to quantum mechanics, we know that electrons can only exist in specific energy levels, preventing them from spiraling inwards.
So, quantum mechanics saves the atom. That's pretty important considering everything is made of atoms. But what other weirdness does quantum mechanics bring to the table?
Another key principle is Heisenberg's uncertainty principle. It states that there's a fundamental limit to how accurately we can know both a particle's position and its momentum. At the same time, the more precisely we know one, the less we can know the other.
Ah, so there's always a degree of fuzziness when it comes to describing the state of a quantum particle.
Exactly. We can't pinpoint both its location and its motion with absolute certainty. It's as if nature has built-in limits on how much we can know about the subatomic world. This uncertainty isn't due to limitations in our measuring instruments. It's a fundamental property of the universe itself.
That's mind-boggling. It's like the universe is playing a cosmic game of hide and seek with us always keeping some secrets hidden. But hold on, didn't you say something earlier about particles acting like waves? That has to be the weirdest concept yet.
It is one of the most counterintuitive but fundamental principles of quantum mechanics, wave-particle duality. It essentially means that particles like electrons or photons can exhibit both particle-like and wave-like behavior depending on how we observe them.
Okay, now I'm officially lost. How can something be both a solid particle and an ethereal wave that seems completely contradictory?
I know it's one of those things that just doesn't make sense based on our everyday experience, but countless experiments have shown that this duality is a real phenomena. For example, in the famous double-slit experiment, particles are fired at a barrier with two slits. Instead of behaving like tiny bullets and passing through one slit or the other, they create an interference pattern on a screen behind the barrier, just like waves do.
So these particles are somehow passing through both slits simultaneously and interfering with themselves. It's like they're spreading out like waves and then collapsing back into particles when they hit the screen. My head hurts.
It's definitely a concept that takes some getting used to. But this waves-particle duality has profound implications for our understanding of the universe, from the behavior of atoms to the very nature of reality itself. And it's one of the key challenges in trying to unify quantum mechanics with general relativity.
You keep mentioning this unification challenge. Why is it so difficult to reconcile these two incredibly successful theories? They both describe aspects of the universe accurately, so shouldn't they work together seamlessly?
You'd think so, wouldn't you? But the problem is that general relativity is a classical theory. It describes the universe in terms of smooth, continuous fields and deterministic laws. Quantum mechanics, on the other hand, is inherently probabilistic and deals with the fuzziness and uncertainty we've been talking about. These two frameworks seem fundamentally incompatible at their core.
So it's like trying to fit a square peg into a round hole. They both describe aspects of reality, but their underlying principles clash.
Exactly. And this clash becomes particularly apparent when we try to describe situations where both gravity and quantum mechanics are important, such as the very early universe, the moment of the Big Bang, or the extreme conditions inside a black hole.
Speaking of black holes, Didn't Stephen Hawking make some groundbreaking discoveries about them using quantum mechanics? That seems like a pretty impressive feat considering black holes are born from the realm of general relativity.
He did one of his most famous discoveries was that black holes aren't completely black. After all, they actually emit radiation now known as Hawking radiation due to quantum effects near the event horizon.
Hold on, I thought nothing, not even light, could escape the gravitational pull of a black hole once it crossed the event horizon. Isn't that what defines a black hole?
That's what classical physics tells us, but when we consider quantum mechanics, the picture changes. Remember those virtual particle pairs that constantly pop in and out of existence in the vacuum of space? Well, if one of those pairs appears near the event horizon of a black hole, one particle might fall in while the other escapes.
It's like the black hole is playing a cosmic game of chance, swallowing one particle and spitting the other one out, and the escaping particle is what we observe as Hawking radiation.
That's a good analogy, and the escaping particle carries away some energy from the black hole, causing it to slowly lose mass and evaporate over incredibly long periods. This process is incredibly slow for typical black holes, but it has profound implications. It means that black holes aren't eternal, and it raises fascinating questions about the fate of information that falls into them.
So black holes are these incredibly complex objects that bridge the gap between general relativity and quantum mechanics. But what about the quest for a unified theory that can explain all the forces and particles in the universe? Is there any hope of finding such a theory, a theory of everything?
That's the holy grail of modern physics. One of those promising candidates is string theory instead of point-like particles. String theory proposes that the fundamental building blocks of the universe are tiny vibrating strings. Different vibrations of these strings would correspond to different particles and forces, including gravity.
So it's like the universe is a cosmic symphony with these tiny strings vibrating at different frequencies to create the symphony of reality. It's a beautiful image.
It is. String theory also suggests the existence of extraspatial dimensions, beyond the three we experience these extra dimensions, would be curled up at incredibly small scales, and their geometry would play a role in determining the properties of the fundamental forces and particles.
Extra dimensions, vibrating strings. It's mind-boggling to think about the implications of these ideas, but it seems like string theory is still very much a work in progress. Is there any experimental evidence to support it yet?
That's one of the biggest challenges facing string theory. It makes predictions that are incredibly difficult to test with current technology. However, it has provided some intriguing insights into black hole physics and the nature of gravity, and many physicists believe it holds the potential to unify our understanding of the universe.
It sounds like the quest to understand the universe is an ongoing journey, a cosmic detective story, with new chapters constantly being written. We've come a long way from the idea of the Earth being flat and resting on a giant tortoise.
Indeed, Stephen Hawking's A Brief History of Time takes us on an exhilarating ride through the evolution of our understanding of the cosmos. It's a testament to the power of human curiosity and our relentless pursuit of knowledge, even when faced with the most mind-boggling and seemingly paradoxical ideas.
This deep dive has been an incredible experience. It's made me realize just how much we've learned about the universe, from the vastness of space-time to the strangeness of the quantum world. But it's also highlighted how much we still don't know. It's both humbling and inspiring.
It's a reminder that there's always more to explore, more to discover, and more to wonder about as we continue to probe the mysteries of the universe. Who knows what other mind-bending revelations await us?
Exactly. So a big thank you to you for guiding us through this cosmic exploration, and to you, dear listener, for joining us on this journey. Keep those brains buzzing, and who knows, maybe we'll have another deep dive together soon.
Loved this video? Smash that like button and subscribe so you don't miss out on future content. And don't forget to order the book, link below.